Teacher,
So, yep,
I want to tell you something.
yep. Anything?
Basically, today is supposed to be my practical, but I overlooked the timetable and I didn't attend.
Huh? Did you attend the practical today?
Yeah, I overlooked the timetable. I was also a bit sick.
Physics?
Yeah.
No wonder I didn't see any practical in your timetable you sent me lah.
Oh, really?
I think so. I see
I,
physics.
I yeah, because I think the timetable I wrote, I missed out the practical part. But the official ones got practical. This one.
So you will lose the practical mark lor. If, if you are
I think
still,
I think I want to retake for during A2.
well, it's going to be challenging.
Mm.
Okay,
But I also got more time to study.
no worry lah. Just put in more
Mm.
effort lor.
Yeah.
This is the definition. Omega is angular frequency, right? It's just the frequency in radian. And then this one is these two are in the formula sheet, right? Just know where to use the formula sheet, oh. And then your V naught is omega x naught. And then if the oscillator starts from the rest position, this is the equation. You differentiate this one, you get this one, no? Okay. X
Mm.
naught is the amplitude lah. Okay. Today we go to energy in SHM. Energy is simple harmonic motion. In SHM, no energy is lost to other form as there is no resistive force. Remember, no resistive force, so no energy is lost at all. Total energy is constant. As the particle oscillates, the kinetic energy is transformed to potential energy and potential energy to kinetic energy. Total energy is constant. Right? So total energy is kinetic energy plus potential energy. Energy is simple harmonic motion. This is an example of simple harmonic motion. A frictionless trolley of mass m is held on a horizontal surface by means of two similar springs, each of spring constant k, and springs are attached to a fixed point as illustrated. This is a partial question, just to show you the. So for simple pendulum, EP is the gravitational potential energy, while for an oscillation, the trolley held by two springs, EP is the elastic potential energy. Okay, for simple pendulum, EP is the gravitational potential energy. For the spring, it's the elastic potential energy. Okay, let's look at the energy. This formula can get from formula sheet. We use the kinetic energy formula, substitute inside there, square it, and replacing the V square, we get this equation. How to interpret this equation? Expand it, we get that equation. So this stands for total energy, half m omega square x naught square minus, this is the potential energy, half m omega square x square. Total mechanical energy, that's your E, and total potential energy, I usually call it EKX square lah, just to associate with spring lah, easy to remember lah. So K stands for m omega square, and it's a constant. Right? So the total energy is the maximum kinetic energy or the maximum potential energy, same thing. How does the graph look like? Energy stored Just remember your spring, half kx squared or half m omega square x square. These two are constant. So it's a parabola. Tension energy is a parabola. And total energy at any displacement is just a horizontal line. Total energy E equals to EK plus EP, where E equals to half kx naught squared. So to get the kinetic energy graph, it's just total energy minus EP from here. So it's just inverted parabola that way. For any displacement, you can take any displacement, the red line. This is a potential energy. There's the kinetic energy. Right? So this is also potential energy. Remember, kinetic plus potential is total energy. This is also potential energy. That distance and that distance is the same. Okay, any comment or anything that's not clear? Okay, no comment, that's
Basically,
clear.
like the AS spring elastic potential energy.
Think of it as like spring, no? The potential energy is like spring, no?
Oh, elastic potential energy. Okay.
1Q à? 1Q, đó bộ thấu như này. Handkerchief. Okay no comment
Mm.
Okay, that is for displacement, right? Kinetic energy with displacement, and potential energy with displacement, total energy with displacement. Whereas displacement time graph, remember it's a sine graph, right? The particle starting from rest position. Right? This is the displacement time graph. The equation is x equals to x naught sine omega t, where x naught is the amplitude, omega is the angular frequency, right? And remember, this oscillator start from the rest position, and the amplitude is constant, right? For simple harmonic motion, amplitude is constant. Energy stored, right? If you remember, if you don't want, you just use m omega square, half k x square is easier to remember, it's like spring. Or if you want to replace the actual formula is k as m omega square, right? So it's easy. If you have displacement time graph, you just square x, square x, that's all. We just need to square the displacement time graph period. This is a period of the displacement time graph. So if you want to write the actual formula, that's the actual formula. Right? You square it. Right? Square this one. So that's how the graph look like. Right? For minimum, this is the period of the potential energy graph. Right? It's half the period of the displacement time graph. Any comment?
No.
Right? This one is the maximum kinetic energy lah. This one. Right? Or total energy lah. Same thing. Total energy is the same thing. Okay, we have drawn the displacement time graph, the potential energy time graph. So the kinetic energy is the other way around, inverted. Total energy is constant. It's just a horizontal line. Where kinetic energy is maximum, potential energy is zero. Right? Potential energy is zero, kinetic energy is maximum. The maximum of kinetic energy and the maximum potential energy is equal to total energy. Okay, using Microsoft to draw is not easy, but I can get from internet. Right? That's how the graph look like. Instead of putting EP, the writer put U. Any question or anything to clarify?
No.
Right? He used A, which is X naught, amplitude. T is a period of displacement time graph. That's how an vertical oscillation using a spring looks like. The interchange, the total energy is the same. Kinetic change potential and elastic potential energy. It's more complex. Okay, let us do some question. So after the break, you also try some question. Okay, this is an old question, but essentially it summarizes what I taught you. Calculate the gain in potential energy when the mass of 150 gram is raised about 1.0 millimeter. Yep, calculate and see what is your answer. Very simple calculation only. MGH.
Okay.
MGH, that's all.
Oh, what's the 10 meters? Oh, yeah, yeah.
I change the 1 millimeter to 0.001 meter. And G is 9.81.
Yeah.
So it's around about 15 there. Draw that. Okay, let's see the next question. In order to set the pendulum into oscillation, the bob is displayed sideways, keeping the string taut until its center of mass is raised vertically about 1.0 millimeter and then released. Using the axis of figure 12, sketch and label that graph to show the variation as the pendulum oscillates or acts with total energy and kinetic energy.
Um,
So instead of just now we are just sketching, but now since they have given you a proper graph, you have to also sketch it properly. No? Right? This is about 15, that's why we draw total energy, 15 there, total energy. This is a potential energy. So there's a graph. So it's just inverted. No? This one is a kinetic energy. No? Right? That amount is the potential energy. So from the total energy down will be kinetic energy. No? That same distance. Same with the two sides. Same with this side. Right? That distance is that distance down. No? Right? That distance is that distance down, lor. Right? It's inverted. So you just draw that, lor. Okay.
Okay.
So that is the amplitude, lor. Right? This amplitude, lor. Okay, no comment, let's carry on. That's how they ask you, lor. What's the amplitude? 40 millimeter. Okay, let's go to 17.3, damp and force oscillation resonance. Right? You can remember the spring, spring elastic potential energy, total energy. When a simple pendulum oscillates in air for some time, what do you observe about the amplitude? Yep. Simple pendulum oscillating after a while, what do you observe about the amplitude?
Amplitude decreases.
Total energy?
Decreases.
Both decreases. Good. Amplitude decreases with time. Total mechanical energy decreases as it transforms to heat due to work done against resistive force. In this case, it's air resistant. Okay, so you need to memorize. Damping is the continuous or gradual loss of energy from the system due to resistive force. Or another way to express it is amplitude decreases as the force is always opposing motion. Either way, right? Type of damping. There's your syllabus. Damp oscillation, light damping. Right? This is called light damping. Amplitude decreases gradually. Right? Amplitude becomes smaller and smaller and smaller until it stops. Total mechanical energy decreases as work is done against resistive force. It's converted into heat. Right? So as it moves, it does work against the air resistance. So energy is converted into heat in the air. Period of oscillation remains constant. Right? That's the period of oscillation. That instant period of oscillation doesn't change. It's still the same. It's only the amplitude that decreases. Right? This curve is exponential. Right? Total mechanical energy for SHM is a horizontal line. So for actual, where there is a resistive force, then the total energy decreases with time. Right? Call it damp oscillation. Total mechanical energy decreases as energy is used to do work against friction or air resistance. Amplitude of oscillation gradually decreases gradually. Okay, how about critical damping? This is simple harmonic motion. Right? Amplitude is constant. So what is critical damping? Object displaced when released return to equilibrium. So that's critical damping. It doesn't oscillate. It just displays, it come back to the rest position without overshooting in the shortest possible time, quarter of the period. No oscillation occurs. Over damp or heavy damping, right? Damping so much that you displace it, it slowly return to the rest position. No? Take a long time. Here the oscillating object is displaced in a viscous medium. It can be oil. No oscillation occur. You displace it, it take a long time to come back to rest. Object displaced takes a long time to return to the rest position. No useful application. Right? We try to avoid it lah. This is one of the experiment your teacher may have asked you to do lah. Study about damping lah. And we use this
Teacher,
one. Yep.
A2 still have practical or not?
A2 is only paper 5. Written practical.
No practical.
No practical. Written
Oh,
practical.
but
That means
written
they
okay.
tell you the instruction, the purpose, the aim of the experiment, and then you tell them how to do the experiment. No? That's question 1. Question 2, they do the experiment for you. They tell you what's the experiment about, and then they collect the data for you. You are supposed to complete the table. No? So here you use a lot of errors. No? So I believe Mr. So hasn't teach you paper 5 yet. Lah. Okay. Uses of critical damping is useful in some system. They use it in the shock absorber or spring. We call it suspension or car. Uses, don't worry about so many of them. Lah. Moving coil meters, the pointer deflect to its value and stop without oscillating. Right? It goes to the value that is supposed to read without oscillating to and fro. Suspension of car system. A good car suspension is one in which damping slightly is slightly under critical damping. As a result, in a comfortable ride and quickly leaves the car ready to respond to further bump in the road. Okay? Not like the old cars during the 60s where you pass the bump, it will go up and down a bit uncomfortable. Modern cars, you go over a bump, it doesn't oscillate. That's why you feel more comfortable. Right? That's picture showing you lah. Right? Just remember car suspension, good enough. No? Right? There's a car suspension. Right? There's your moving coil galvanometer. Just treat an info lah. No need to bother so much. What is force oscillation? This girl is performing force oscillation. Memorize. No choice. Force oscillation occurs when a body is made to oscillate by the application of a periodic driving force. Key is periodic driving force. That means the force follows. Push, let it come back and push again. That's simple pendulum. Periodic. There's a force applied at regular interval. It's a simple harmonic motion, but driven externally. Amplitude remains constant as energy is provided by the periodic driving force. Right? Periodic driving force is the external force. Right? Example of this two boy lah. Right? Simple example of force oscillation is a child swing. As you push, the amplitude increases. Right? As this boy, the driver, this is driven, it push, amplitude becomes bigger and bigger. When the swing is displaced and released, it oscillates with the natural frequency. Right? You can time it and find the period, and then from the period you can get the natural frequency. While sitting on the string is a driven oscillating system. While on the ground is the driver, periodic driving force. Due to damping, the amplitude of oscillation decreases. You push it, you find slowly the amplitude decreases because of air resistance. To keep the amplitude constant, the driver, this boy, must push at the right time. That is the swing is about the swing hours. Right? So as it comes there, you push it. As it comes back, as it's going down, you push. Right? So energy for this system is supplied by the driver. That's why the amplitude stay constant. The driver provides the energy to the swing. Any comment or anything not clear? Any question?
Teacher, so I can say amplitude is directly proportional to energy.
No, why you bring that one up? Amplitude is if you think of potential energy is half kx squared.
Mm.
Okay, not directly
Yeah.
proportional. The proportional to x squared.
Oh yeah, okay.
And the frequency of the driver is the same as the natural frequency of the driven oscillator. The oscillator oscillates with large amplitude. Damping or resistive force limit the maximum amplitude. Why cannot you increase the amplitude indefinitely? Keep on pushing, you keep on adding energy. Why can't you increase the amplitude after a certain time? Amplitude looks like constant even though you push so hard. Any idea?
Um, why cannot decrease? I mean, why cannot
Why
increase?
cannot increase the amplitude? You keep on
Even though
pushing.
the boy pushed the swing other.
The boy pushing the swing up to a certain time, certain frequency, certain amplitude, you cannot increase it anymore. No matter how hard you push. Use your physics principle to explain. Can
Hmm.
for low velocity, the damping force is proportional to speed. But for high speed, the damping force is proportional to speed square. So more energy needs to be provided by the driver to increase the amplitude of oscillation further. Right? So that's why you are being defeated. At higher speed,
But it's still possible, right?
I don't think so. Because the higher speed you use, the greater will be the resistive force. Unless you use supernatural strength. But that's very dangerous.
Oh.
Okay. This extra knowledge only lah. Nothing much about in the syllabus. Resistive force of that's a resistive force, that's a motion oscillating object moving to the right, and it's proportional to the speed. At higher speed, that resistive force is proportional to speed square. More and more energy is required to increase the amplitude. What is resonance? Okay, in 10 minutes time we have to
Natural
stop.
frequency.
So while we stop, we do some of the question there lah. At resonance, the oscillation of the object is at maximum amplitude when driving frequency f equals to natural frequency of the object. Right? So at resonance, the object is at maximum amplitude. So the driving frequency equals to natural frequency. Right? Oscillator oscillates with maximum amplitude. The driving force is the one that supplies the energy for the oscillator to vibrate with maximum amplitude. The constant amplitude can be also maintained by half natural frequency that is pushing the swing in alternate periodic cycle. Right? When the person comes, you're supposed to push. The first time you push, the second time you miss it lah. So alternate lah. So that also can keep the amplitude constant lah. So how does the graph amplitude against frequency looks like? Right? Without damping, it will be very large, oh? Right? Undamped. Light damping, right? This heavy damping. Stop me if I'm going too fast.
Yes.
F naught is the natural frequency. You can obtain it from just determining the period of oscillation, oh? 1 over the period. Sketch the graph to show how the amplitude of oscillation varies with frequency of the periodic driving force. Right? That's slightly damped. Just repeating only. How can you increase the damping in the experiment? Increase the surface area of the oscillating body. No? On the same graph above, sketch the curve of heavy damping. That's heavy damping. No? Right? Natural frequency doesn't change. This for your info only lah. The sharpness of the resonance depends on the amount of damping. Being sharp for light damping. That's what it means. Light damping very sharp. For heavy, for heavy damping, the amplitude of the oscillation at all frequencies is reduced. Amplitude is reduced, the peak becomes flatter. Yep, amplitude becomes flatter for all frequency. Why is the driver jumping up and down? Why is the diver jumping up and down on the springboard? Try to explain on what we have just studied.
Oh, I can only think of gaining momentum. More driving force?
Basically, she's trying to cause the springboard to oscillate or vibrate.
Okay.
So if she can get the springboard to vibrate at natural frequency, then the amplitude of the springboard will be very large. So the board will push her to the highest point. Then she can dive, lor.
Oh, okay.
Do more somersault, lor. Okay. Benefits and troublesome. This one is for info lah. If you don't want to study, don't study, lor. It's not in your syllabus anymore. In some situations, resonance can be useful, but in other cases, it's troublesome. Right? Benefit, useful application to resonance. Your resonant tube, lor. You amplify the sound. Musical instruments rely on resonance to amplify the sound produced. Right? Tuning fork is very soft. So at resonance, you can hear the sound of tuning fork. Lor. Resonant vibration of quartz crystal are used to control clocks and watches. Right? I just go briefly lah. Electrical resonance occurs when radio circuit is tuned by making its natural frequency for electrical oscillation equal to that of the incoming radio wave. That can receive the incoming radio wave. Right? Won't bother about all this anymore. Lah. Right? Can read yourself. Lah. Troublesome. Soldiers need to break step when crossing certain suspended wooden bridges. Failure to do so would cause the loss of over 200 French infantry in 1850. Tacoma Narrow Bridge disaster in 1940 was caused by bridge being too slender for wind condition in the valley. Right? When they built it, when they built the bridge, they didn't use a model and then use a wind tunnel. So when the wind blow at the right frequency, the bridge becomes oscillate. So, okay, so you won't bother about all that. You want, you can read that yourself. Since it's not in the syllabus. Okay, let's go to a bit of paper 5. That's what's happened. Tacoma Narrows
Oh,
Bridge Then after that, it break into two, lor. Break into pieces. Lor. Okay.
The teacher, resonance is for sound or wind also can, like air.
Wind basically provide the driving force to cause the
Uh-huh.
bridge to oscillate. Okay.
Basically, the wind is just blowing the bridge, right?
The wind is blowing, but it has a certain frequency,
Which
certain.
causes the impact to double, is it?
So when it becomes equal to the natural frequency of the bridge, then the bridge will oscillate with high amplitude. Lor. Yep.
The wind frequency,
Wind frequency.
same as the bridge natural frequency.
Mm. This is an example of force oscillation. No?
Oh, I thought it's the sound only can happen.
Sound is also pressure, changes of pressure.
Oh, okay.
Okay, this is more for paper 5. Right? This is your analog lor, signal generator. Our lab one, I think we have digital one. Lah. It provide you this different waveform lah, only for those interested in study electronic or physics higher form lah. But we are interested in the red one only lah, red waveform. Other name oscillator, low voltage AC source or power generator provide different waveform in the form of alternating current used in ripple tank experiment, force vibration. Allow different frequency amplitude of sinusoidal waveform to be selected. Now it will be cut off at any time now. Right? The voltage can be changed, can be increased or decreased. Okay. Have you all done this experiment? That is your spring. I
Yes.
don't think so. This one is taken from past year paper, November 1997. Where this
I think we got two. Quite.
got do not bad a teacher. That's your spring, no? That's the block of mass, half meter rule. That's a marker, pin, and the retort stand. Variable frequency vibrator. Both spring are under tension as they are extended from the rest position. Right? The variable frequency vibrator allows the frequency of the vibrator to change. You change the frequency using the power generator. The vibrator,
Oh, we don't have the frequency variable frequency vibrator and the pulse generator. We
power
just shake it
generator,
ourselves.
we got, it's not
No, no,
shown.
we just shake it ourselves. We pull ourselves one.
Oh, you pull yourself. You can
The way
use
we did it.
electronic power generator to
Oh,
do it Right? So that's the amplitude. That's the driver. Amount of damping, you can just put a cut below. No? There's a mass there. The cut below there. Take a cut.